background so basically we have two types of parameters in Rietveld refinement. One type has a sound physical basis. Another type is empirical, and I think this is the problem why Rietveld refinement doesn't work in all cases, especially when we have violation of translational symmetry. So let's consider some of the structural imperfection, and let's have a look what kind of effect they will have on powder diffraction patterns. Matteo Leoni earlier today already showed the violation of 3D symmetry. Here's just another take on it. Let's consider our old friend graphite. So we all know the structure. I don't think I need to say anything about this. And diffraction pattern from this structure would look obviously like this. And then let's just cut out a small piece from this big chunk of graphite. So in 3D it will look something like this. And the diffraction pattern will be somewhat similar to what we had originally, but with a broader peak, and the peaks actually broadened anisotropically, which is hardly surprising, since this distance is greater than the distance perpendicular along the planes. Well, let's not stop here and try to mess up with the structure even further. So let's cut it more, but let's don't stop at that. Let's push the layers apart. And in addition, since this is not, well, as if this is not enough, let's rotate the layers randomly. Let's say the lower layer to some random angle clockwise, and the middle layer to another angle counterclockwise. And this is how usually the semi-ordered region in turbostratic graphite looks like. And this is something that I pinched off the web. It's just the structure of the turbostratic graphite as some people imagine it. So when we look at the diffraction pattern, then the change will be much more drastic in this case. As you can see, there are fewer peaks, and they're much broader, and they are of peculiar shape. And if we just consider Rietveld, yes, and this is how the peak positions are shifted. I will talk about this a little bit later. And if we try Rietveld method, so for this pattern, obviously, Rietveld refinement will be straightforward. For this one, well, difficult may be a too strong word. Here, slightly difficult it will be because there is an anisotropic broadening. But with the modern software, you can do this very easily. As for the top pattern, well, this question is pretty rhetorical in my view in this case because this is the obvious answer. So why is that? Well, first of all, since we broke the symmetry quite dramatically, the intensities of interplanar and intraplanar peaks are not correlated in terms that we can't use a simple 3D unit cell to calculate their intensity. Another problem here is that we have quite complex and pretty uncertain intraplanar peak shapes, which are in this case 1, 0 and 1, 1. Why is that? Well, we can consider how these peak shapes look from ideal graphitic layer that are different only in diameter. So the order is perfect, but the size of the layer is different. And as you can see here, obviously peaks become broader, but there's this peculiar shape where the fade out on the high to theta angle is pretty slow. And another interesting feature is that the maximum position of the maximum count actually shifts to the lower d spacings. And if you look in the literature, you can find quite a lot of people who ignore these shapes and the fact that the order was broken, treat this as three-dimensional peak and claim that they have different lattice parameters within the plane. Okay, but it is still possible sometimes to do some kind of a Rietveld refinement, at least on parts of the structure, because great scientists like Warren, in collaboration with Bodenstein in 1966, derived this equation which describes this type of peak shape. And it is not empirical equation, it is derived strictly from a single secular graphitic layer. And this equation does work sometimes, and I will show you now one of the examples. Some 20 years ago, I collected this pattern from a hexagonal boron nitride, which obviously, as you know, each layer consists of a honeycomb arrangement of boron and nitrogen. And here is the same peak, which is this one, collected at with a different radiation. And using Warren-Bodenstein approach, it is possible to get a fit like that, which is pretty decent. And from this, we can get the radius of the ordered region within the plane and the lattice parameter, which corresponds to the lattice, not surprisingly, to the lattice parameter of bulk boron nitride. And this is the position, if we had three-dimensional order, this reflection, which will be in this case 1, 0, 0, the maximum will be in this position. But unfortunately, as usual, life is not that rosy all the time. So if we go back to graphite, and if we consider just small particle of graphite of this size, consisting of 16 layers in a perfect stack in ABAB, and then, once again, if we rotate each layer randomly, then the peak shape changes like so. And if we compare this red peak shape with the peak shape just from a single graphitic layer, they don't match that well. So basically, in order to use something like Rietveld, you need somehow derive the true peak shape function in order to get sensible result every time for each particular case, which is kind of impractical. Okay, let's look at some other things. Some 25, 30 years ago, I worked with nickel nanoparticles, 16 nanometers in diameter. And what we noticed at the time, that peak shapes of the non-oxidized as prepared nickel particles looked quite all right, nothing unusual. But when we oxidized them by several atomic percent of oxygen, they started to look like this. And well, this is obviously just the part of one of the peaks, but all peaks looked pretty much the same. So we needed somehow to find out why. Why is that? So in order to do that, we extracted the true profile, because this is what we observed in the experiment. And as you know, that what we observed in experiment is an integral convolution of instrumental function and the true profile broadening. So by solving this integrated equation, integral equation, oh, sorry. Well, we obtain these true profiles, and as you can see, in the case of non-oxidized nickel particles, we had two satellites of the similar height, while the satellite on the left-hand side for the oxidized particles was essentially higher than on the right-hand side. So we had these patterns, so the obvious question was what to do next with it. And here comes the first time that I will mention the equation of Debye. The red color of the previous slide was meant to wake up if someone fell asleep. Quite a while ago, you saw this picture of Peter Debye in both presentations, I think, of Bill David, as far as I remember, exactly the same picture, although the difference in this case, I think I've got his full name. In 1915, in this wonderful paper, written in German, he derived this very simple and elegant equation using which you can calculate each point in a powder diffraction using just atomic form factors in case of X-rays or neutron scattering lengths in case of neutrons, and distances between all the atoms in the scattering domain, and of course wavelengths is also included there. The beauty of this equation that it is exact, that it takes that it is exact in the firstborn or kinematic approximation. Details of what is firstborn approximation was given very nicely by Laurent Chapon in his first talk. And this description deals explicitly with Bragg and diffuse scattering as well as small angle scattering from a powder. So then it was pretty straightforward after that. We created a model particle, which means calculated all the coordinates of all atoms, then calculated distances between them, stuck them into the formula, and got these three shapes. So we did it for three types of particles. The first one, we just took the normal bulk structure of nickel, just a small particle. Then we non-uniformly contracted and non-uniformly expanded it. And as you can see, non-uniformly expanded particles, the diffraction peak shows the similar features as the oxidized particle, which led us to the conclusion that the change of the shape that we noticed was caused by of the nickel particle due to insertion of oxygen, and non-uniformity of this deformation can be explained by higher concentration of oxygen in the surface area compared obviously to the core. Hardly very exciting results, probably very predictable, but anyway, it was nice to get some kind of diffraction confirmation for that. Simon Billings in the previous talk told you all about nanoparticles, problems, and so on and so forth, which makes my life a little bit easier. So I will show you a more recent example, and this is an example of TiO2B nanotubes. This appears to be a very important material as anode material for future lithium batteries. And you can readily synthesize these nanotubes. Here the TM is shown, and you can see that the outer diameter of the tube is 100 angstrom, in is 46. And when we look at the diffraction pattern, it looks like this. Hardly the prettiest thing you've ever seen. But nevertheless, even at a glance, you can probably guess, and it would be a fair guess, that there is severe anisotropic broadening here. And this we can confirm if we calculate, if we superimpose the diffraction pattern calculated from the bulk structure. The bulk structure looks like this. I won't go into details, don't have time. So it's a monoclinic structure with these lattice parameters and space group C2 over M. So, and if you look at these two patterns, you can see that if you broaden some of the reflections and broaden them to a different extent, you will get kind of similar pattern what we observed in the experiment, which was a good starting point for us. And furthermore, if you look, luckily, the narrowest reflection was a single one, 0 to 0. And if we just use a Scherer formula, that gives us the size in the direction 0, 1, 0, which is about 140 angstrom. And if you look at the sizes of the tube, the only way that, that we can place the B-axis here is along the tube, because obviously this size is greater than even the outer diameter of the nanotube. And of course, later on, it was confirmed by electron diffraction. So with this starting point, we know where the B-axis is, we know the exact geometry. So it was a simple matter of getting TiO2B structure into this shape and somehow preserving some kind of a motif that was in the bulk structure, but at the same time get it disordered. So there are three basic ways of doing this. One thing, we can just take the bulk structure, cut out a cylinder first of this outer radius, and then drill a hole. Unfortunately, this doesn't. It's not a good approximation, since we have more symmetry than we bargained for, because the anisotropic broadening in this case will be much less severe, since we have a perfect translational symmetry across the hole. So this model is not good enough. Another way would be obviously to take just a thin slab of the structure and bend this layer into Archimedean spiral. Why Archimedean? Because obviously we would like to have the same distances between subsequent turns of the spiral. But by doing that, we lose radial registry, unfortunately, and this means the 0,0 reflections will disappear from the experimental pattern, and this is not the case. So this didn't work either. So the third way, from the obvious ones, would be just to take a slab of the structure and bend it. It can be done like this, or it can be done this way, and we need to bend it in such a way that the average distance, the average d-spacings along the circumference, well, and in all other directions for that matter, should be the same as in the bulk, since we didn't see any significant shifts in our experimental patterns compared to the bulk structure. So by doing this, we obviously have a severe expansion of on the outer side of the tube, and severe contraction of the same magnitude on the inner part. So after that, it was the matter of creating this type of segments and filling up the tubes. Well, it's basically you place all atoms on some kind of imaginary lines perpendicular either to the A for this case or perpendicular to the C axis, like in this case, and then create geometrically nanotube and take these lines and place them in the radial direction. And this is to emphasize that in the middle of the tube, the distances are exactly as in the bulk structure. So by doing this, those two fragments start looking like this, and then we can take these fragments and fill up the whole tube. While doing this, we needed to readjust slightly the radius in order to get a seamless junction, but it was just a matter of solving this transcendental equation, not a big deal. So we've got these two tubes looking like this. Obviously, these were first created with just one unit cell size along B, and then we translated it 37 times in order to get the B value that we obtained from the Scherer equation. And we've got these two models. One contained almost 73, another one 67,000 atoms. And the next step, obviously, we calculated the Debye patterns from each of those models. And as you can see, there are more peaks here than in the bulk TO2B and correspondingly in our experimental patterns, which is hardly surprising since we've got the ideal tube. We impose some kind of asymmetry across the whole, which actually didn't exist in the original TO2B structure. Also, when we compare these two patterns, if we just once again try to broaden these peaks, this pattern would match the experiment better than this one, especially if you consider this area or this area. So this type of folding was discarded at this stage. And of course, in order to reduce the number of peaks and make peaks broader, the obvious things would be to cut the ordered region from the full tube just to a kind of a segment. And we tried different number of segments. This is a single segment, 2 segments, and we found out that the best fit, it's a little bit difficult to see from this pattern, but the best fit was obtained with 2 segments. However, some intensities didn't match experiment very nicely. And when you think about this, it's pretty obvious why. Since we are dealing with nanotubes, the experiment was done in Bragg-Brentano geometry. So the tubes obviously would tend to lie in the plane of the sample holder. In order to account for this effect, we introduce an additional term in the Debye equation, which I borrowed from retooled refinement. This is March-Dawley's correction. Only in this case, the alpha angle is the angle between the line connecting I's and J's atom and the 0, 1, 0 direction, which is along the nanotube. So by kind of a grid stage, or rather trial and error, we tried different values of T1, which is a variable parameter, and we found that the best match we get when the value of the parameter is 0.8. Of course, this is not refinement. This is just gives you basically the overall idea that the overall shape kind of matches the experiment. But it was good enough for our purposes, because if we compare the pattern calculated from our non-uniformly deformed segment and ideal segment, we can definitely tell that this is not ideal. It provides much poorer match to the experiment. And this actually has pretty important consequences. We can explain electrochemical properties of these materials much more readily using the deformed structure. So, in the end of the day, this is the whole tube, and this is the ordered segment within a tube. So basically, each tube consists of a number probably of these segments that are not in registry with each other. But of course, we would like to do a refinement. Everyone wants to have nice fits and reliable results. But before even contemplating any refinement, we need to find out how long does it take to calculate diffraction pattern using the equation of Debye. So if we have n atoms, this gives us almost exactly n squared divided by 2 interatomic distances. And if we take the previous example of the ordered region in the nanotube, which contained 7,664 atoms, which gives almost 30 million distances. And if we consider that our diffraction pattern was 4,000 points, then, and we have just our desktop machine, then it will take this long to calculate a single diffraction pattern. This is quite impractical, especially if you consider that during any refinement, you need multiple calculations of diffraction pattern, and it's hundreds of thousands. So I will leave it to you to estimate how long will it take. So we need to look for the ways how to speed this up. There are three basic main ways of doing this. First would be to decrease the number of points in the pattern by either reducing the range or increasing step size, pretty obvious. Probably reducing the range is not such a great idea. We can increase step size and we can gain something from this. Another way was suggested in 1991 by these authors in this journal, which I don't think exists any longer, is to replace the double sum in the Debye equation by fast Fourier transform. They showed a nice example, and it works for larger particles, but according to my experience, when we switch to smaller particles, this approximation is not precise enough. We actually getting quite biased diffraction patterns. And the third way would be head-on approach, basically make a parallel code and employ a multi-core computer. So this one, I think, better be discarded. So what we can gain here? Realistically, we can get probably 5-10 times faster due to this approach. And this, it depends what you have access to. So if you have access to supercomputer, you can make it thousands of times faster. So these were two approaches, by the way, that we use, as you will see later. This refinement actually is still ongoing, so this is kind of preliminary results. So go easy on me with this one. This is once again the same phase of titanium dioxide, but the geometry is particles rather than tubes, as it was in the previous case. And this was reported as nanoparticles of spherical nanoparticles of 3 nanometers in diameter. We repeated the synthesis, and the size, well, roughly corresponds to what was reported, but there's no way that these particles are spherical, although, once again, it's not easy to see it from here. But if you stretch your imagination a little bit, you will notice some of the particles here, although they're merged, but there's no way they're spherical. And the diffraction pattern looks like this. So once again, it's the same phase as the nanotubes, and this is the bulk diffraction pattern from the bulk. As you can see, the broadening here not as anisotropic as in the case of the tubes, but nevertheless it is still there. Because if you just remove the tubes, you can see, for instance, that this peak and this peak have roughly the same half-width, but this peak contains only one reflection, while this contains two, and they're pretty well separated. So there is some degree of anisotropic broadening. And if we take a closer look at this TM image, and we actually looked at God knows how many, we can find kind of particles which resemble ellipsoid shape. Of course, I mean, it requires a stretch of imagination, but this was the best that we could come up with. So on to refinement. The refinement procedure here was simulated annealing, and at the first step of the refinement, we took just the lattice parameters of the bulk, created a chunk of the structure, and cut out a sphere. I use these 3 diameters because this will become the axis of the ellipsoids in subsequent subsequent steps. So we cut out this sphere, calculate distances between all the atoms in this model. This is just 3 atoms shown. And calculate diffraction pattern using the Debye equation. Calculated the chi-square. then calculated the increments for random increments for parameters in the next step. And the fit, the initial fit looked like this. Once again, not the best fit that you've ever seen, but actually considering that this is head-on ab initio, this is the pattern calculated from the basic principles. Once again, it's not such a bad starting point. So on step 2, after we applied those increments that we determined in the previous step, obviously I will exaggerate slightly the effect of these increments, the magnitude rather of these increments. So the pattern was shrunk like this, and then we cut out an ellipsoid. And then we calculated, once again, distances between the atoms. But in this case, we didn't consider atoms as stationary and occupying the same ideal position. What we did, actually, we replaced the point position for each atom with the, well, here is shown ellipsoid, but we took sphere in the first instance. And every time any of the atoms was involved in calculation of interatomic distances, this distance was chosen randomly within this predetermined sphere. And the sphere size, sphere diameter or radius was also a variable parameter, one for titanium, one for oxygen. Once again, calculated diffraction pattern, calculated chi-square, use Metropolis scheme to either to accept or reject the step. This was explained in detail in Ken Shankland talk on the global optimization, so I'm not going into details here. And once again, calculate the magnitude and the signs of random increments for the next step. And once again, the next step, the same procedure, only the structure becomes slightly better. Ellipsoid is located, well, the vertical axis is longer than the horizontal axis. So it was the other way around in the previous step. And once again, exactly the same procedure, and so on and so forth. So after 24 hours of doing this, we used the 12-core desktop. Actually, it's a server from Dell. We installed Unix there, and it worked fine and parallelized the code. So we calculated approximately 94,000 trial patterns, from which over 11,000 were accepted. And after 24 hours, the system froze. And froze in terms of simulated annealing, not because it went down. We had the precautions. We bought the universal power supply, so we were well prepared. Anyway, the fit looks like this. Lattice parameters didn't change much, which was kind of comforting. Obviously, I mean, it deviated from the original idea that all the particles were spherical and 30 angstroms in diameter. So it's along C, it's almost 40 and about 25 in the other two directions. The mean square displacement, the amplitude of the mean square displacement was about 0.5 for both titanium and oxygen, and the chi-squared became, well, 4 times less than it was initially. So this is just a comparison side by side. And as I said, it's a pretty primitive model at the moment. Actually, while I'm talking here, hopefully my workstation is calculating now by it's doing refinements using more sophisticated model with the deformation matrix and so on and so forth, because as Simon Billinge mentioned, strains and deformations are not unusual in nanoparticles. So maybe when I come back home, I will see better fits. But it works, it is simple, and you can, using the Debye equation, you can compare your calculations directly with the experimental data. So I think I will stop. I will stop at that and better leave maybe more time for questions. Thank you very much for your attention.
I didn't want to stop you. You had 5
No.
minutes. Okay.
I was talking too fast, probably.
Okay. Any questions? Thank you for your talk. Yes, please.
So I start with the question, so no one seems to place others. Thanks for the talk. I would have a lot of questions. I just reduced them to basically 3. The first one is concerning the Debye equation, basically one. You said that you also get the small angle scattering out of that. This is not correct. You got the small angle scattering for isolated particles. So when you do the experiment, it's wrong. The other 2 things is, did you consider, for instance, the model of Whittaker for cylindrical lattices, 53, 54?
Could you please speak up? I can hardly hear you, to be honest.
Just 53, 54, Whittaker presented a model for cylindrical lattices. Did you try to use that one?
No, I haven't. But as I said, this is basically the beginning of this work. This work is pretty much ongoing. So,
and the other thing is that there's also other possibilities to speed calculation up instead of just doing the parallelization.
I'm not denying this. Actually, there are obviously other ways, and actually I'm well aware of, I think you're the author of that paper about using the graphics cards and so on. So there are plenty of ways of speeding it up. I mean, this is just, I wanted to give some idea how in principle you can do that. So I'm not arguing with that at all, and I didn't consider those 3 as the only ones.
And the last one is, what is the reliability of the data you extract with such a high noise?
Yeah, that's a good question. I think in retrospect, this school should be called, can we trust any of the powder diffraction data? Obviously, this is a major question that you can ask. And we are not doing just diffraction. We are collaborating with computational people who are trying our models, and hopefully they will also